proximity och grejer. Prova att skanna den här då. Då får du upp liksom hela ditt liv så här. Det kommer på
Okay, welcome everyone to this first parallel session where we will talk about AI. Before we start, I'd like to inform you that you can ask questions to the speakers using menti.com and the code you see there, 61586353. So you can ask the questions during the whole presentation and we will take them after the presentation is done. And that's also for our online audience. They can also send in their questions on Menti. Well, now you're going to get some presentations about different AI applications that have been produced at Mid Sweden University. So I'd like to introduce our first speaker, Jan Lundgren.
Thank you. So, practical AI applications. We have a bird's nest in here. So I'm going to start a little bit just talking about experiences with AI in practice from, let's say, our research topics. And then Markus and Adam will tell you a little bit about their specific projects that they are doing in industry. So it will be even more specific. But I will start with a little bit of an overview. I didn't think I would tell you what AI is this time. Maybe you already know some of it. We basically use AI and machine learning to find trends in data. What are the trends so that we can then make predictions, classifications about different like parameters in data. The first thing I'm gonna put up is a lot of topics that are good to consider when you do an AI implementation. And not all of them are connected only to the, let's say, the technical coding of the neural networks and everything. There are a lot of things around it. So the ethics is a big part, and that is something that you need to consider early. What kind of data do we have? Are there any ethical ethical questions about the data? Are we is it patient data? Are there any IDs? Can you identify people? These kind of the birds are very close. Yeah, they're getting closer. Getting a little bit. So that's a big part of it. What I am also trying to convey to my students is to have the system perspective, so that you're not only focusing in on the neural network and like coding that model, but you need the whole overview. Are we replacing humans? Are we trying to do something that humans do today? Or are we trying to do something that humans cannot do? Like, what is the data? We're going to have a look at the view from outside. How will this be perceived when we're done? What kind of margin of error do we have? Is it enough that we have a 90% accuracy? Does it need to be 95? Does it need to be 99? And finally, something that I think Markus and Adam will talk about as well, AI or not AI. What do we need? Do we need AI in this implementation or not? Maybe we are going there just because. So if we talk about the system perspective, this is the part that you would think of when you talk about neural networks and machine learning, the network setup and the training strategies, basically. But then there are so much about the data as well. What kind of data are we getting in? Do we need to process it to further enhance the performance? Do we need to augment it? What does that mean? Augmentation basically means that it usually means that you kind of fabricate data that are like simulated data alongside to the measured data, so that you get a larger pile of data, let's say. And also, like, just labeling IDs we've seen has a huge impact as well on the final outcome. As if that was not enough, then you have everything around it with the hardware. You're getting the data in through the sensors and the readout electronics. Do you need to do some noise reduction even before it comes into the networks? And all of this needs to be considered. Also, one thing is, depending on where you're implementing AI, you need to worry about how it will be received when it's done, when it's there. So I will take a case with classifying heart sounds as an example that we have been looking at, where we have digital stethoscopes. So we basically record heart sounds and then try to say whether a heart sound is normal or not. Just those two. So that if it is not normal, we can send that person to an ultrasound scan. So right now in that field there is a kind of a gap between the technology side and the healthcare side. So the technology side looks 50 years ahead and thinks that, okay, we're going to replace all the specialists. There will be only robots. That is not received very well by the healthcare because, well, they want to keep their jobs. So instead, we try to promote AI as a support tool, so that it can be seen like for decision making, or as a training tool for, let's say, cardiologists that have just come out of school and they are very new to this. And I think that much of our role will be to also bridge this kind of gap. What is the job? This is something we need to think about. Are we emulating a human doing something? I mean, it could be possible for a human to actually classify a heart sound by listening to it. It's very, very difficult, but it can be done. Not always, though. But it has to be a very experienced specialist. Are we trying to surpass humans? Are we trying to do something that is impossible to do? Finding trends in a huge pile of data that will take us, I don't know, 30 years to sift through, and that a machine can do it in 30 seconds. And this also will make the implementations very, very different. I would say that this is probably the most common right now, because this is where the most ideas comes from. You have a case where you see that this guy standing with this machine can hear that something is wrong, but he's only there for a couple of hours every day. You need something that can listen to this machine 24 hours a day. That is the kind of ideas that comes up. So emulating the human, but doing it all the time. Are we using the direct measurement as data, or are we using a more soft sensor case where we don't have the measurement that we want, for instance, but we have a lot of other data connected to that parameter that we are interested in. In the case of heart sounds, we tried both. Either you classify directly on the heart sound, or you have a lot of other data about the patient, blood pressure, just the age, just if it's a man or a woman, has correlation to whether it's going to be a normal heart sound or not. So all of these parameters have, like, I think it was 10 or 12 different parameters. Even excluding the heart sound itself, you can make a fairly accurate prediction if the heart sound is going to sound normal or not. So what we did there was that we had two different strategies where we classified directly the heart sounds and then this soft sensor strategy, because this gave us 91% accuracy. The problem we saw was that we had some false negatives, which means that the model said that the heart was fine when it was not, and that is the dangerous part. So that is what we used this soft sensor solution for. Came in, and in the combination we got that number, that error down very, very low, like under 1%. So that's also a thing that you can think about. What in the classification is the most important not to miss, let's say. Yeah, just some graphs of what you can expect from this kind of measurements. So you can see, like, you can get up to like 80% accuracy even without the sounds themselves. But the classification from the heart sounds will be over 90. And the reason for this is that we take the sounds and we make images from them. So we make spectrograms. So this is actually the heartbeats that you see here. Dum dum, dum dum. And this is on the time scale, and this is on frequencies. So the higher up you are, the higher the frequencies. And then the color is the intensity. and then you can use convolutional neural networks to see what you can find, if it's a normal one or not there. I would say also that we are working with the quality of sound, and we are right now looking into beamforming, where we can direct the microphone array, so we're using more than one microphone, so that we can listen to one specific heart valve, let's say. And then we kind of remove the noise from the lungs, from the veins, everything else that we are not interested at the moment. And that gives us, in that case, we got the noise down by 16 decibels. And if you know anything about sound, you know that 16 decibels is that's huge. That's a huge number. So that is interesting. Something that we're looking into for the future. Yes, I think that was my talk. We are moving on to Markus.
Thank you. My name is Markus Fält, and I'm an industrial PhD student at Försäkringskassan and Mittuniversitetet. And I will talk about practical AI applications within what I'm doing at Försäkringskassan, which is about anomaly detection in IT system logs. And sort of, I want to describe the problems there. First, overall, about what is the problems in the large-scale IT system industry, and then look at what can anomaly detection do, and what is the problems with anomaly detection. So today we are seeing that large-scale IT systems are transitioning from traditional physical on-site kind of state to a more dynamic mixture of both on-site systems together with cloud systems, together with off-site systems. And we're also seeing that a lot of more systems are being run completely on software-defined resources. This means that the system is not running on the machine, it's running in a virtual environment. And this has made the overall structure of the sort of IT environment more complex, and it has increased the amount of configuration that is needed, which has led to more complex log data and a lot more log data. IBM, for example, has estimated that the amount of log data has increased by a factor of 2 or 3 every year recently, that is generated by these kind of systems. And also this is a trend that was, I think, was seen a few years ago by Gartner. They coined the term AIOps, which I have put up there, which is about AI or artificial intelligence for IT operations. And this is just about what we're talking about, which is we're seeing that the systems become more complex and sort of a little bit unmanageable to only do manual analysis on them. So where in this sort of process can we use AI? And I have a few examples here. We will be focusing on anomaly detection, but we can look at intrusion detection, where we are trying to identify, for example, a malicious actor that is getting access to a system. Root cause analysis, this is when you try to ask, you sort of view the system as a patient and you ask why. Why do we have this symptom? For example, why is the patient coughing, or they have a sore throat? Why do we have a sore throat? And this is also something, when we talk about system, we have to look a lot about at the underlying information that the system generates. Summarization, this is the system might create huge reports of data. We might want to have a quick overview of this data or this log report. So how can we summarize this data? How can we highlight the important parts? How can we remove the redundant information? And lastly, anomaly detection. This is a general method for just finding something that is deviating from the norm or not normal. But before we talk about anomaly detection, I just want to sort of simply talk a little bit what is a simple, in a machine learning we call this a binary classifier. What is a simple binary classifier? And the binary classifier is that we have two classes. In this case I've chosen cats and dogs, and we label them. So we have labeled cats as 0 and dogs as 1. And we want to give the model an example of a cat or a dog, and the model gives us some type of output. And this output is in the range of 0 to 1. Closer to 0 means it's a cat, closer to 1 means it's a dog. So when we're training the model in this case, we put the picture in, we get our value out, and then we compare it with the original label. And our goal is to update the internal structure of the model so that we get better and better estimations of the class label. But we see that in this case we have two well-defined classes, we know what they are, and as long as we have enough time and enough pictures of cats and dogs, we can create a huge amount of training data for our model. In the case of anomaly detection, however, we have the two classes we are interested in is normal and abnormal. These are a little bit more abstract to talk about, and we maybe in the terms of abnormal, the problem with this is the nature of what is abnormal. Well, it means something that's not normal, and how do we define abnormal samples? And this is a big problem. We might be able to run our system and we can see when an abnormal sample happens, but this system, might be a small part of the possibility of abnormal events. We might be able to see an abnormal event, but it might be difficult to imagine what an abnormal event. So it can be difficult to create these by just like we did with the cats and dogs. So instead, in anomaly detection, we often just want to be able to train a model only using the abnormal data. But here is the question: how do we? Now we don't have a class 1; we only have a class 0. How can we get the model to learn something different than just predict 0 every time? And this is where it comes, we have to look at the internal data. So for example, in log events, the data might look something like this. We can see that, for example, what I have been doing work on is looking at the sequence of events. So we might try to look at the sequence of events. We predict the next event, and now we have a pair. We have a predicted next event and we have the actual next event. And we compare these two and we calculate some type of anomaly score. So how close are these matching each other? So we will get something like that. And then to see what is the abnormal and what is the normal, we have to plot it. So we would have time like this, and we could potentially see, okay, here we have a good separating line between something that happens quite rarely and the normal case. And that's sort of the method that I have been doing, at least. And setting this threshold can be very difficult as well, because if you do not have a clear gap like we have in this case, it can be very difficult to find the correct threshold to set. And it might be multiple parameters, not just one value that you have to search through. So recently we have done some work about this, and at Försäkringskassan we tried to create such an anomaly detection model using log data generated from a testing system. And this system was doing sort of simulated work. And then during the testing process, we injected anomalous, or we injected unexpected events or unexpected behavior at certain time points. And then we wanted to see, okay, if we train this model on some of the, what we would say is the normal data, can we create a model, or can we see that that model is able to see some difference between the normal and the abnormal? And what we ended up with, after we trained the model and everything, we saw something like this. So here we see we have about 6 hours of data, and this is log data that we look at the sequential order of them, and we detect anomalies in the sequential order of events. And we see here that the gray regions, they represent where we expect there to be anomalies, and the white region is just normal data. So this model was trained with a small percentage of the normal data, and we saw that it was able to quite well detect at least 2 events. One event was detected with about half confidence, and see we have a last event there that was not detected at all. Now this might be because we have too few features. We are only looking at the sequential order of the events. There might be more information. For example, if you work with log data, sometimes there's a lot of information in log data. We have English words, we have parameter values, we have identity numbers, we have IP address, and so on. So what we're looking at now is how can we create a better pre-processing process to include more of this data that's contained in the log lines, so that we can potentially improve this. So I want to conclude by saying that anomaly detection, especially in IT systems, it's difficult and it's because of the unbalanced nature of the problem. We have a lot of normal, we have no or almost no abnormal data. And we can usually train on only normal data, but we need to look at the features that are available to us. Can we somehow quantify, can we compare a prediction with what is really happening? We need to ask this kind of question. And lastly, anomaly detection is quite a general method. So if you are able to do that, I think you can jump quickly to some other more advanced topics. For example, looking at, can we detect intruders in our system? Can we use this to help us in the root cause analysis process? Or can we do summarization? That's all I have to say. Thank you for listening. So now,
hey. Hello. Hello everyone. My name is Lundström, and I'm a industrial PhD student at SCA. I'm also part of Smart Industry Sweden and SSC at Mittuniversitetet. Today I'm going to give an overview of AI in condition and predictive-based maintenance. So I think let's jump straight into the problem at hand. This is a very simple sketch of a fan in a factory. And we can view it as a system. It has several different components. We have an engine, we have a belt, bearings, we have rotor blades, and we also have other things such as a damper. And the thing is that if these components relate to each other, and if one fails, the system fails, right? So we will have downtime. And this is a major problem in the industry, because unplanned downtime leads to huge amount of costs, especially in industries where we have one line production, where basically when we have unplanned downtime, we can't produce anything, right? So this is a major problem. So how do we address this problem? Well, one way is to use sensors and signals to try to measure the health status of these components and thereby the system as a whole. So we have, for example, pressure, flow, temperature, vibration, sound, current, speed, and several other ways as well, right? And in terms of machine learning applications, which is a major part of AI, these are the types of signals that we can actually use to build something that helps with this problem. So we have, for example, fault detection and classification. And in this area, we're looking at trying to connect patterns in the data to particular events. So for example, a type of bearing fault, we use historical events, and we try to generalize from those. So next time there is a fault in the bearing, we can recognize that, well, this is that particular fault, right? We also see remaining useful life application, and this is very valuable when it works. Very challenging, but when it works, it's very valuable, because we can basically calculate when is the end of the life for this particular component or system, and so we can do maintenance on time and save a lot of money. But it's very challenging. We also have anomaly detection, which Markus has already explained. It's very similar in this area, but other data. So what we do here, especially for deep learning solutions, is that we basically try to learn from the normal behavior, and then be able to separate normal from abnormal data, which often is related to faults or at least certain events that we are interested in finding. And I'm confident that machine learning has a major part in the future of this area. But at the same time, we need to be careful not to become too optimistic of what we can do here, because there are several challenges. First of all, well, in many in the industrial context, what we often see is that faults are very rare, which is a good thing. But it means that we have very few examples to work with, to learn from, related to these different solutions that I've just pointed out. And in addition to that, data is what we can call heterogeneous. And what I mean by that is that if we take one fan and look at the data there, and then look at another type of fan, another place in the factory, we're going to see differences. Okay, so we have different noise levels. We can find other types of faults that we did not see in fan 1. There could be other types of sensors that give different values, and it could be that, well, the fan is not the same fan. It's similar, but it's built differently. So the data will not be the same. And what this means for us is that it's very difficult to build a model here in domain 1 and just simply transfer it to domain 2. Because in many cases, what we will see is that the performance will go down. Okay? So with that in mind, and I'm relating this to what Jan spoke about in his first presentation, I think we need to understand the potential and challenges with the different types of solutions available from a strategic point of view. And we also need to ask ourselves, okay, what do we want? What do we need? We don't need to build something super complicated if a simple solution works. So if we look at this area, we usually talk about 3 different major solutions. So we have data-driven solutions, which, I mean, machine learning is a part of. We have physics-based solutions, where we use known theory about how, for example, components relate and where we usually see faults and stuff like that. And we also have knowledge, which can be gained through expertise about how different machinery works, what certain events are extra important for us in this context and not as important in this context. And just to give you an idea, this is sort of an overview where I'm working towards right now, where I'm trying to utilize machine learning solutions in the domain-specific part, where we learn the behavior of that particular system or component, and we can also improve the performance using human interaction. We can get an anomaly scores, we can get root cause analysis in that stage, and then we can use more, based on that, we can use more general types of methods. For example, rules. We could use statistics, ML, and physics-based methods to get very advanced decision support. So that was all I had to say, and thank you for listening.
So thank you. We got a lot of questions here on menti.com, so I will ask the questions for you, and feel free to send in more questions if you have. So the first one I will direct to you, Janne. Can you explain the two terms of AI and machine learning in contrast?
Oh, that's actually a very good question, and I would say no one has an absolute answer to that, because everyone has a different definition, kind of. It's subtle changes, but let's say if I take a mean value out of all the definitions, AI, standing for artificial intelligence, usually means that you're using neural networks, which are models, tiny models of our brain, more or less, or a simulation of how a brain would work. Machine learning, some of the machine learning uses neural networks, but you also have like support vector machines and, let's say, older or earlier models that don't use neural networks. So you can say that machine learning goes across these methods, but AI usually means the involvement of neural networks. Then you have deep learning, which is also something that I think most people define as when you go from a case where you tell the models what is important in the data to a case where the models themselves start to decide what is important in the data. So they are themselves looking for features, let's say, I would say.
And the next question is to Försäkringskassan, so I guess Markus will answer that. Do you use anomaly detection to expose frauds?
Right now, this is I work in the system management and IT operations. I have heard this about, but I don't know if this is necessarily done at other parts of Försäkringskassan. But where I work, we are strictly dealing with the with the system and trying to see is the system behaving as it usually does. We don't know if it might be related to a fraud or something, but we don't know that. So we are just looking at the system as sort of a black box. It produces some data, but we're not looking at the sort of cause of that.
Okay, thank you. So I think this one is for you, Adam. If you don't have a lot of abnormal data, is it possible to simulate that and thereby get more abnormal data?
Good question. Good question. I would say yes in some instances, but at the same time, it's difficult to simulate the real scenarios. If we need to also always consider that for example, if we consider there's a bunch of open access datasets from simulations, and when we've, for example, tested on rigs in a lab, we get a lot of data and we know exactly when there's a fault, so we can measure the performance of a new solution. But the problem is translating that to a new problem. So it's very difficult, I would say. And in addition to that, I mean, in some cases, in some applications, I would say that it's possible to easily induce faults. But if we look at the main specific part in the industry, I mean, I would love for SA to start to induce faults in machines, but obviously they don't want to do that. So we are left with what has happened before, and in many cases there is not a consensus exactly what was the cause. So it's very difficult. I mean, to get label data in the real industrial context, at least for some applications, can be very difficult. Yeah.
Okay, and then I got a question here about is the anomaly detection works requires NLP? I don't know who feel to answer that one.
So especially if you're depends on what feature you're looking at. But if you're looking at sequential features, for example, natural language processing we are usually looking at sentences and word orders, and a lot of that research has used similar types of models, and I have to say we take a lot of inspiration and use similar methods there. Right in the model the model that I showed that had the results, it was a transformer model. This is there's many different types of models you can use. One is called LSTM, and in this case I just picked this one to show we have results for LSTM as well. They perform similarly on this kind of data. I would say that a transformer model seems with today's sort of computers where we have graphics card that can do big kind of big multiplications of vectors and matrices very fast. Transformer models seem to be faster than old, but LSTM models that are processing the data in a sequence, while in a transformer model we can process the data in a more parallel stream, kind of.
I can fill in one thing as well, which I think is interesting related to what Markus just said. My experience so far, which I think is interesting regarding the different algorithms, is that oftentimes similar types of setup works fairly good in other domains. So, for example, convolutional neural networks, as Jan talked about in his presentation, used to be, used a lot for image recognition, right? But for example, in my area, time series area, we're also seeing a lot of convolutional neural networks. So so there's a lot of similarities actually in that regard, I think, in different fields.
Yeah, we got a follow-up question. Is it possible to use unsupervised learning in anomaly detection?
Yeah, that's basically what we're doing. So we're training on. I guess it depends a bit on the definition, because we assume that the data we're training on is normal. So in some sense, I guess you could say that it's semi-supervised, but nevertheless, yes, it's unsupervised. So we learn from normal data, and then we don't have any we don't have any examples of anomalies in the training procedures. So only
basically when you don't know what you're looking for, you call it unsupervised. Yeah. You can say.
That unsupervised usually means that you have no labels. When we're doing anomaly detection, we usually assume we have one label. Yep. So I would call that a one-class classifier. In unsupervised learning, we are not trying to sort of create a classifier. We're trying to learn something about the data. So I would not call this unsupervised, but it's sort of in the same area, I guess. It's a blurry line between them.
Yeah, I think at least in my field, the definitions. Some call their solution unsupervised, and some call it semi-supervised. So it's a bit different, but yeah.
Then I have one question for Janne, I think. In AI applications, how can you say my trained model is performing accurate by 90 or 95%? Especially in medical applications, maybe 99.99% accuracy is not enough to trust the AI.
Yeah. So that is also what I was talking about. How accurate does the model have to be? So I would say, if you are not allowed to make mistakes, don't use anything, I guess. This doesn't apply only to AI. If you have a person there, of course there are going to be mistakes. So what you start thinking about in that case is, how accurate do you need to be? How accurate is the system or the person in place right now? What do we need to beat, let's say? If a person makes an error in 8% of the cases, can a machine learning model do a better job than that, or a worse job, let's say. So usually it's in that area. But I would say if you have a 99.99% accuracy, it's very hard to go beyond that, because usually if you end up with 100% accuracy as a result, you have made an error in your coding, usually.
Yeah. To a final questions. Many organizations are planning to start using AI or are interested in using AI. Do you have any tips for them how to begin?
How to begin? Wow. So this is my answer to this has changed over the years as well. So I would say, I mean, coming to us as an institution to make an inquiry whether we can help to make an investigation if AI would be possible in this case. This has proved very valuable to many of our partner companies, because what we have seen is that someone at the company knows that there are so many cases here where we could be helped by AI implementations. But maybe there's a resistance somewhere, or you don't really know where to start. So what we try to do is we go in and we try to find a good case. Mattias did this with Biometria, for instance, and that turned out they are just expanding that side of the business model right now. So you find a case where you can let's say that we call it the easy hard. You know, it seems hard, but it's okay. You can implement an AI model and you can get a decent result, so that you can show what kind of value you can get from this. And there we can help, or there are other companies as well, third party, that you can collaborate with as well, because it's very difficult to have AI competence everywhere on all of the in the industrial companies as well. Yeah, I would say.
Yes, thank you. I think our time is up, but you will be here during the day. So if you have more questions, you can ask them directly. We didn't have time to finish all the questions, so I guess there are some more. So I say thank you very much to your speakers. And now at 11:30, we will start a new session here that's called Challenges in the Energy System. And in the other room, it will be Skogens värden. So you have these two sessions here to choose from, and we also have the parallel sessions at Good Tech Conference. So you have the schedule outside. So thank you so much for participating. tänker hela tiden att jag ska slå på den, men det behöver jag inte. Ja, akta de här så bara inte snubbla på. Jag har försökt tejpa fast dem lite grann, men... So, welcome everybody. Now it's time to start our next session, Challenges in an Energy System. Quite high topic area right now. And before we start, I like to mention once again that you can ask questions to the speakers by going into menti.com and use this code 61586353. And that's both for you here in the room and the one who's following us online. So I'd like to introduce our first speaker, who is at the grid company Vattenfall eldistribution, and she is also a former student at Mittuniversitetet and studied the power system engineering program. So welcome, Yvonne Ruwaida.
Thank you very much, and very fun to be here. And I just want to warn you, this is about the challenges in the energy system, but not about the price challenge. If you have questions about that, ask them later. I'm going to talk more about the technical challenges that we are working with every year and that are changing even when the energy system is changing. So what are the trends that affect electrification and that also changes our challenges? So, for example, we have production that is disappearing. We have new, very huge actors like data centers, battery industries, and of course EV chargers, the big ones that are coming. The cities are growing a lot, and we also have renewables coming into the energy system. And then we actually have a very old grid. The grid on the transmission side is actually due to be repaired now everywhere or to be renewed because it's actually it's so old. So all this together gives the background of the challenges. And then we have, of course, the climate issue, and where the energy system with the Swedish fossil-free electricity is challenged because all the existing traffic sector and the industry sector, they want to use electricity so that we will become fossil-free. So I'm with the grid company, and the grid companies, we are dimensioning our grid. And it's power that is the dimensioning. So energy production and, for example, the power balance nationally and also the frequency, they are not issues that are dimensioning the power grid. Of course, some of these issues affect, but for us it is about power in every point in the grid. And the grid is from the local side up to the transmission side, has a lot of points. And in every point, you have to have the right dimension. So the difference between energy and power, just an example very fast for ones here that doesn't know that. I hope everyone here does know it. So the energy in a battery, for example, 23 kilowatt hours. If you have slow charging, it takes 7 hours and the power is 3.7. But if you have fast charging, for example, 50 kilowatt, then it takes 30 minutes. So the power, that is what we have to dimension the grid for. And dimensioning the grid, you have to understand also that in every point of the grid, we want to manage one fel, one not wrong, one not mistake, one what do you call it? Ett fel I nätet? Anyone? One error, okay. The biggest error, we have to work with that in every grid. And why? Because we want to have energy of supply. So we don't have to have customers don't get their electricity. And this is the challenge when we are planning. And also we are planning for a very long time. And what's happening today, no one talked about that 15 years ago, or even 50 years ago. So building grid takes a long time, and the higher up you are in the grid, the longer time it takes. So for the transmission grid, it can take up to 15 years. In the regional grid, it can take 7 to 10 years. And in the on the low grid, it can take 1 to 2 years. But sometimes, actually, it can take up to 7 years, even very down in the grid. But mostly because you have problems then on the regional grid. So And also what's new in the planning in Sweden is that before we had the same kind of flows in the grid. Now a lot of flows are changing because production and consumption is changing, but also you have more export-import from other countries because you have more cables to other countries. And the grid was actually dimensioned for having water power in the north and consumption in the south. This is how the Swedish grid has been dimensioned on the transmission side. And when this is changing, when you get flows from Finland to Norway and UK, so you get the flow from east to west, this is not, the grid was not dimensioned for that. And even flows going from south to north is not dimensioned for. And this actually could be a reality in the future. So when we look at this dimensioning hour, I think there are very few hours that are dimensioning. So here you, for example, see what's happening when you have the lowest level in the grid, and here when you have the mid-average, and here the highest level. This is one regional grid in Sweden. And also, so between seasons, it differs a lot. So to understand what we're dimensioning for is actually something that happens very seldom. We talk about a 10-year winter. And just also to show a little bit about, this is a 3-year power in Uppsala region. And here you see that very few hours you have this highest level during these 3 years. And here's actually a regional grid in the north of Sweden, not far from here, not far from Sundsvall. And here you see that this is a different grid because here you have consumption and here you have production. So in the regional grid, sometimes you have more production, only production, and not consumption. But even here you have some hours that are dimensioning on both sides. And the biggest challenge is that we have the electrification with these very, very big new consumers. So for example, a battery fabric, 300 megawatt. I mean, all the politicians said everywhere, oh, come to us, come to us. Yeah, we build the Uppsala next to Uppsala because 300 megawatt is as much power as you need for the whole Uppsala. So building, just putting a battery fabric or a big data center somewhere that is actually as huge as the city itself, that is not easy. That's not something you do in 1, 2, 3 or 5 years. And also you have smaller data centers that can be around 50 megawatt, 20 megawatt sometimes, or 5 bigger fast charging stations where you have perhaps 10 fast chargers. They can be 50 megawatt. And this is a smaller city like Enköping. And if you want to compare with something else, it's half the capacity of a regional grid, 70 kilowatt. So 70 kilovolt. So I mean, these are huge sizes, and I think that understanding this has been a little bit hard for the society. So if I then go from the grid, I'll go to the transmission grid. And the transmission, the TSO, they have 4 main challenges. They have the power balance nationally that I talked about before. And this is actually not a big issue in Sweden, even if it's now has been discussed a little bit. I think you've heard about that we could have 150 hours in Sweden. We will not have the power balance. And I would say this is 150 hours that probably will not happen. But if they happen, we will know about them the day before. And we have a lot of means to work with it. We have resources to work with it. But still, it's a new situation because if you go back, we did have 5 or 10 hours calculated, not 150 hours. And also, if we would have a problem with the power balance nationally, the consumer would know about it in advance, and they would get curtailed for 1-2 hours. It would not be like if you have a big storm and then you would have no electricity for a day or a week or something. It will be like more organized. But this is what you read about in the papers, discussed a lot. And then you have the frequency. I think Viktor will come to that. He's working with services for the frequency. And you have the system responsibility, and there are a lot of things in that. And then you also have the capacity in the grid. And I must say, power is complex. So these, of course, they have, you know, things going together. Just some years ago, 3 years ago, we would say, like, we have the problem with capacity in Stockholm, Uppsala, Västerås, Malmö. Some perhaps becoming problems in other regions, and here in the north, it's green. But unfortunately, we have to move the green one to the first level. So now we actually have the biggest challenges in Sweden here in the north. I don't know if you have read about it, but we have so many big actors wanting to be here in the north that actually now this is this is the region. I work a little bit with this region where we have to work with capacity solutions. And flexibility that I work with is one of the tools that we are going to use to try to be able to connect more customers faster. So what is flexibility? And it's called, it has a lot of names. They're also called demand response. And I think we use the names differently. But now on the EU level, when we talk about demand response, we talk about everything. Production, consumers that are changing their behaviors because you have a signal from the, for example, TSO or DSO. But it can be also energy storage, of course. Before, demand response was more limited, but now we use it in a broader sense. So someone is changing their behavior. It can be a price signal, but it can also be like you are purchasing. And this is something new. Purchasing capacity is not something we've been doing a lot in the past, and not on a DSO level, but this is something that I work with. And then you also have something called conditioned connection agreements. This is also a tool in a toolbox that we will need to work with, and the rules of these is worked at on the EU level and on the national level as talking. So they are not finished, so the rules are not really there yet. This is actually a problem for us a little bit, choosing, you know, solutions without knowing how will the regulation be. So what happens when you're purchasing? It's very simple. You have someone who says, I have something to sell. For example, I can be flexible in my consumption as an industry, or when I charge my cars. And you sell this to a marketplace for flexibility. And the grid owner on their side, they work with knowing when they need this flexibility. It can be the TSO and it can be the DSOs, and then they purchase it. And we had demonstrations in Sweden, several of them now. But the first one was actually the demonstration of coordinate. It was in Uppsala, Gotland, north of Sweden, also in Malmö and Skåne, where we actually worked with the first local flexibility markets for capacity in Sweden. And on these markets, you sold to the DSO, but you could also sell to the TSO. You could sell frequency services, ancillary services to the TSO. So what kind of flex could there be? And actually there's a lot of different types of flex. Aggregated heating pumps in industries that are bigger heating pumps in energy companies. You have a lot of reserve power. Water power can also, hydropower can also be flex. Gas turbines, CHPs, aggregated chargers, for example, lights in växthus, greenhouses, energy storages and energy communities. But also in the future we see other types of possible flex resources, for example vehicle to grid, data containers, hydrogen and so on. But I think the most exciting game changer is the digitalized aggregator, and this actor has actually been working in these flexibility markets. For example, in Genic and Tibber, aggregating chargers, aggregating heating pumps, aggregating cooling, and they actually sell this aggregated to us, to different markets. So they work with value stacking. So for example, they have some kind of benefits for the owner. That can be temperature control, for example. It can be working against the subscription, optimizing the subscription for the company. But then you can also then sell it to the local markets. You can sell it to the wholesale markets, but also to the balancing markets, MFRR, FCR, and so on. And this is actually an opportunity, but it demands a lot of coordination between the markets. It demands that you have, it should be simple to participate on these three markets. It shouldn't be pre-qualification that differs, because then it will be a lot of work. And this is something we are working with the rules on the national level and on the EU level to have rules that could be used. So at the moment, for example, we're working with communication when you are calling for flexibility, to have a branch standard for that in Sweden. So that, for example, if an aggregator wants to be in both Sundsvall and Luleå and Malmö, doesn't have to have different kind of APIs for different DSOs. And actually, if you go back in time, what did the DSO do when we had flexibility? We used the telephone. Go just 4 years back. The only way for a DSO to purchase, to call for flexibility, was using the telephone. This will not work. I mean, we are actually supposed to, for example, document everything we're calling for. To do that manually is very hard. And if you have a lot of resources, like in Uppsala, we have like 500 households and 10 buildings and 2 industries and 1 energy company. I mean, calling them all from the from the operator doesn't work. So you have to work with the digitalization, and this is something that there's a lot of feelings about this. Some people say, "Oh, but I mean, can someone having a charger have an API? Don't we ask too much?" And it's a learning process, you know. And I say, for example, it's not ICA and Konsum who will have the API. It will be the one having the charger, or the one having the service of paying. Someone will be the one who will have this on a national level, selling this service to the customers. But it's a change movement in your head, understanding these kind of things. And also as a DSO, it's hard. I mean, oh, shouldn't we steer the consumer? I mean, having a business model telling them that we are calling for them doesn't feel safe. Can we really trust it? So it's really change management on all levels. So this is what is needed. And if you go then back, so this is a new role for the grid operators. Like if you go back, we worked as a distribution network operator. And we built and operated and renewed grids. And now we have to work as a system operator with a lot of more tools, like the smart digitalized DSO. So I would say, coping with the challenges in the energy system, we have to get here to the system operator. We are called system operators, but we are not system operators yet. We are doing this in demonstrations, large-scale demonstrations that we are continuing with, but we're not yet doing it whole scale. In Sweden, we are good in metering. We are, like in the European Union, one of the best countries coming to how far we've come in metering. But in regard of working as a system operators, we are still new beginners. But this is going to be an exciting journey into the future, meeting those challenges in the energy system. So that was a little bit introduction.
Here we have the content information also for later on. So I am Kent Bertilsson, professor here in power electronics at Mittuniversitetet. I will mainly discuss some of the problems that will occur in the grid, and then Viktor here, industrial PhD student, will go into details about how that is implemented. As Yvonne said, we are going from an earlier implementation of the grid where we have a static centralized generation, big power plants distributing the power to the customer down in the grid. We are moving to a more decentralized generation. We have smaller power plants distributed within the grid, and also that will reverse the power flow. Before, the power always went from the generation source to the down to load. Sometimes now it will go in the opposite directions and so on. As Yvonne also mentioned here, we need to measure a lot. We need to control things dynamically in a completely different way than was needed in the earlier grid. With the energy storage will be a very important thing in order to handle the demand and response, so that we can balance out the difference between generation and the consumption. So one example that will occur in the normal system, where we have always where we have it was designed for closer to transformer, further out on the line, the voltage is dropping, because the power direction is going from the transformer and out to the grid. But nowadays, lots of customers, they would like to place solar power far out in the grid. A problem will be when it is a sunny day in the summer, low consumption, the power flow that is reversed. And that means that if you before you had it was designed for this operation, the voltage rise instead on the power line. And of course then the neighbors here, they will be very angry because their television sets is damaged and so on. So you need to do some modification there. What you could do dynamically or static is you could change this transformer with the tap changer and so on. Either you can use it manually, or can be done dynamically also in slow variations. You don't have that remote on that many places far out in the grid. The problem is also that if you have a big solar installation and you have a cloud passing, this situation is changed in a few seconds. So you need to have equipment that can handle these kind of things dynamically. And instead of going from larger and bulky dumb transformers, you can go to more intelligent solid-state transformers. So this is more or less a power converter instead, but then you can dynamically control the turn ratio from pulse to pulse. Another interesting, more closer and perhaps more robust design is also this was called an LVR, line voltage regulator. What that can do, then you have a small series transformer in the power grid. This series transformer can add or reduce delta T or delta dV or delta voltage. You're taking power from the grid, you're feeding it to the series transformer, and then you can add or reduce the voltage. So then that you can handle dynamically in a way, and this can react much quicker. And it's also closer to an iron nail solution, so it's more robust and so on. Another thing that occurs in the power grid is when you're having large plant is suddenly removed from the grid. Then this will react in the grid that the frequency will drop, because the frequency is typically held by large rotating objects in the grid, and the inertia of these ones. And if you have a sudden change in the production and reaction, it will respond in the frequency. And this frequency, if you detect such frequency difference, you try to mitigate that by fast increasing the produced power into the grid. This is typically done in earlier days with the water power plants. And if you detect these water power plants to increase the production, the water power plants, they need a few seconds to react. And before this, to take this fast derivative and to get more power in, the Svenska kraftnät have in the recent days starting to upphandla this fast frequency reserve, so that you introduce power much quicker into the power grid when you detect these frequency variations. And this is what Viktor will discuss. And what we do compared to typically you using battery installations and to generate lots of power. Supercapacitor, we have done some research at the university, and when you only need the energy for the first 5 to 10 seconds before the water power plant can start to inject power, it is much more cost efficiently if you can use supercapacitor instead. So that is what Viktor will tell you more about.
Okay, so now I'll try to tell you more about this thing called frequency regulation. So I'm going to present the project Fast Frequency Reserve from Hydropower. My name is Viktor Döhlen. It's a joint research project between Sollefteå kommun, and they own a power plant called Sollefteåforsen. That's where I work, and I'm conducting research here at Sweden University. So I'm going to talk about what is frequency regulation, zooming down a bit from the broader grid perspective that Yvonne presented and Ken presented. Setting the context of hydropower and frequency regulation historically and today. What are supercapacitors? Why do we want to use them as the energy storage? And then draw some broad strokes on the scope of the research project and present some preliminary results and try to keep within the time so we have time for questions. So I'll jump right into what is frequency regulation. We were talking about frequency dips, how to mitigate them. The frequency is to be kept exactly at 50 Hertz. And how do we do that? We do that by keeping production and consumption exactly the same in every second. But I've drawn out some frequency data here from a few days this summer, end of June, beginning of July. And what we can see is that the frequency is never exactly at 50 Hertz. It always deviates a bit. So the TSO, or the transmission system operator, Svenska kraftnät, they have some tools to mitigate these frequency dips. And they're called frequency containment reserves, for example. And they are resources that either increase the production or decrease the consumption, or decrease the production or increase the consumption to mitigate these kind of frequency deviations. So if there is a surplus of electricity in the power system, the frequency goes up, and if there is a shortage, the frequency goes down, and the containment reserves try to counteract this deviation in frequency. So these reserves always sense what is the frequency and how should we act. And the frequency FCRN is one of these resources, and it acts within this shaded area. So if the frequency is within these limits, the frequency FCRN automatically activates. And then we have some other frequency containment reserves that are reserved for if there is a pretty serious frequency deviation. It's called D for disturbance. So if the frequency goes above 50.1 or below 49.9, the FCRD should be activated. And we're talking about what's happening in the power system. We're getting more converter-based generation, less generator-based production. And I've illustrated kind of how this affects the change in frequency in this pedagogical scale that I've drawn here, with two different bases, where you can say that a power system with lots of generators producing electricity has kind of a wide base. So if there is a dip in production, the scale won't tip as fast. But if we have a power system with lots of converter-based generation, this base kind of shortens, and the system needs to be balanced more actively and faster to counteract dips in frequency. And that's why we introduced, or Svenska kraftnät introduced, FFR, which is the fastest balancing service. Then we also have slower reserves, AFRR and MFRR, which I'll talk a little bit more about later. And I talked about the name of the research project is Fast Frequency Reserve from Hydropower. So we're going to kind of focus on this FFR and also the FCRD. So historically, hydropower has contributed to the bulk of the regulatory power needed. But with the changes in the power system, the frequency containment reserves need to be activated faster. The FFR is too fast for these old hydropower plants to contribute to. So they can't really access the fastest regulatory service anymore. And here you can see what happens if there is a dip in frequency. All these different regulatory power resources are activated at different times. First, the FCRN kicks in, and then the if it's a pretty serious frequency deviation, the FFR kicks in fast, then FCRD. And these resources are usually not that endurant, so the AFRR and MFRR kicks in to restore the frequency back to 50 Hertz. You might wonder, what's this geometrical shape with blue? It's my illustration of my workspace, the Sollefteåforsen. I'm actually pretty satisfied with the illustration. So the basic outline of the project is then we have this power plant, which is a pretty old Kaplan turbine-based power plant. It doesn't have the response time needed to act on these fastest system services. And we want to add energy storage and power electronics so that it can inject power almost instantly to the power grid. What are the benefits? So you get a faster response time. You then get access to more regulatory power services, these three here. If you combine energy storage with the hydropower plant, it's cheaper than a standalone energy storage system. And you also cause less wear and tear on the hydropower turbines. And you might ask yourself, is this really new? I've seen lots of installations of battery power in coordination with hydropower plants, and that's correct. A lot of actors have actually done these kind of installations, but they've used batteries instead of supercapacitors. And batteries are the go-to technology when it comes to energy storage. However, we kind of see the hydropower as the large battery in this situation. It acts as the energy reservoir. So we just want to scale the energy storage after the power needed to provide this difference between what's needed to qualify the power plant for the fast system services. And then supercapacitors are a viable option since they have a very high capability of discharging current. So batteries are great at storing large amounts of energy, but supercapacitors have very high specific power. You don't need that many supercapacitors to get very large currents. So you can kind of slim the energy storage if you like. So we want to dimension the energy storage after the short durational FFR. This is the shortest and the fastest of all the regulatory power resources available to the TSO. It just is active at nominal power for 5 seconds. And then we want to investigate, what if we coordinate this very slimmed down energy storage with the hydropower plant to also qualify the system for FCRD, which were some of the other system services. And the system dimensions we're looking at is a 5 megawatt nominal power output for 8 seconds. Because if you look at this FFR resource, you have a ramp up time of 1 second, 5 seconds active nominal power, and then ramp down of 5 seconds. So with some basic geometry, that you get 5 megawatt for 8 seconds. We also want to look at how do we integrate the supercapacitors in the multi-level in the converter in a suitable way. So it's a kind of development project as well. So I'd just like to present some preliminary results. In this left graph here, I've plotted what's the requirements to provide FCRD. It's this blue line here. And what are some Kaplan turbine responses? How fast do they react? And I have one fast Kaplan turbine and one slower Kaplan turbine. And then I've taken the difference between the blue and the red and the blue and the yellow and plotted this in the right-hand graph. So this is the energy, the integral of these graphs are the energy needed for the system to provide FCRD. And this blue graph is the FFR requirement. So if you compare the energy needed, you can see that if we dimension the system for FFR, this should also be able to provide FCRD in coordination with a hydropower plant. So that's good. And we want to investigate this further. And I talked a little bit about converter design. So one of the points of the research project is to develop a converter for this application. And we've been looking at multi-level converters, which normally handles very large voltages, and the use cases are normally HVDC. But in this medium voltage case we have 5 megawatts. We want to supply it to a 10 kilovolt connection point. We see that there is a possibility to increase the number of sub-modules and use low voltage components, because the smart thing with the multi-level converter is that you can split up the voltage in one of these phase arms so that the semiconductor components in each sub-module only needs to handle part of the total voltage. And here we want to integrate the supercapacitors in parallel or in series, and which configuration is part of our research project. And we've done a MATLAB model of this whole converter with the integrated energy storage to see if it works, and we get some satisfying results. We're pretty interested in the junction temperature in the semiconductor as we're using low voltage rated components. And we see that we do meet the temperature requirements for many of the cases. And I've highlighted some of the best simulation results here in this graph. I'm not going to go into why we chose this over-dimensioning is to make the system resilient over a long time. And I will conclude by saying that all of this is the number of supercapacitor modules needed to supply this energy, and we have between 50 to 68 sub-modules in the multi-level converter. And this is a project size that would fit in one 40-foot container, so it's possible to do this quite dense, you might say. And the cost is ranging between a bit above $400,000 to a bit over $800,000, depending on which technologies you choose. And this is also quite competitive compared to battery systems. If this system would be able to supply FFR and FCRD, it's a pretty satisfying result. So with that, I'd like to conclude. Thank you.
So thank you very much, all three of you. We have got some questions here from menti.com, and you can still send in your questions if you have any more. I think this one is for Yvonne. The politicians are hinting at expanding nuclear power in Sweden. Are the grids prepared for that?
I mean, depends on where you put it, like everything. So of course, production is positive in many places, but you always have to have the grid built for what you're doing. So even for production, you have to have the right dimensioning of the grid. So it always depends on where you're putting production or consumption to understand if the grid is prepared or not prepared.
Thank you. And here is also one question. Solar power on villas and buildings and industries are increasing. will that be a problem?
Yes. And no. Depends on what you're doing. And I was a little bit thinking about what you were saying, Kent, because you were talking about possibilities of having, for example, some kind of solution for voltage control now in the product, for example, solar power. We have to have the correct business models. We don't have them today because, for example, if you have solar power in a grid and the grid is built for consumption, and now you get a new dimension in criteria. Summertime, when the sun is shining and you have low consumption, do you want to build the grid extra, it costs money, for 1 or 5 or 10 dimensioning hours? I mean, voltage control is a little bit different. Or do you want to find solutions where we have more smart grids, smart business models, so we don't have to renew grid and make them less effective? So I mean, this is really an exciting area, and I see a lot of things being done in this work that can actually help the grid of the future.
I can comment also that one, and this is a thing that is coming from Sundsvalls elnät, that they have at Bosveden, I think they have installed free at the bostadsrådet have installed 3 big 500 kilowatt solar installations there, and Sundsvalls elnät is very afraid how to be able to really ensure that they can handle the power quality or the voltage quality, so that they don't see over voltage and under voltage, especially under voltage, because it's more unpredictable when the sun is vanishing, if you don't know that. But if you have cloud passing and so on, when the sun comes back, you always have the possibility to ramp up the power easily and so on. And the tap changer transformers, they are not built for always go up and down in voltage range. So they have purchased this LVR system, and they will place it for in Ånge to start with, and we will start also to investigate that one, and if it is a satisfactory solution. And it's a cost-efficient solution compared to making a more intelligent transformer, I would say, for lower power.
Okay. And another question here. How does increased energy consumption command works for balancing frequency?
How does
increased energy consumption command work for balancing frequency? I'm not sure.
It's more about, I would say, no, I wouldn't say that you have more consumption, that it will create more problems for frequency, but I would say that we have consumers that act differently. So, for example, if you look at heating companies, before you would as a grid planner, you would know how they would act. They would have, but now we don't know anymore because they optimize different resources and they participate on different markets. And then the consumer in itself actually makes it harder to understand what's happening in the grid. So we need more coordination, we need better rules in how to interact and act, because otherwise we will have problems with frequency, for example. So I wouldn't say that more consumers, it's not going to be a problem for frequency. It's more consumers acting differently that will be a problem.
Yes, and I think we can take one last question. Will these applications perform well in more sunny countries? Will it require more smart grids?
I mean, I think you could say that in Australia, for example, they have had a very large expansion of their solar power, and they've experienced lots of challenges in handling such a power system. And I heard someone working at an Australian DSO, and he compared like the Australian power system to a jet fighter versus another power system which has more stable resources to like a Boeing 747, because you need to be a lot more faster with your balancing and have really good control over the balance of such a system. So if you do have lots of renewables, then you need to be active with your balancing. But yes, these kinds of solutions are definitely part of or necessary to have such a power system that can function.
And then, of course, we also introduce lots of control system out on the grid. Everybody is reacting on the same frequency signal, so it's important that you don't overbalance, so that you're starting to create oscillations and so on. So it's an interesting challenges we have in the future.
Yes, thank you.
Thank you very much.
Thank you.
Yeah, thank you.
And thank you. Now we will have a lunch break, and we will start again at 13:30, and here we will talk about remote controlled timber loading, and in the other room it will be talking about schysstare käk in Swedish. So I welcome you back 13:30. Thank you.
För varje fordon eller fordonskombination i rörelse så finns det ett flertal lagar som man måste förhålla sig till. Det måste finnas en förare som i varje ögonblick har kontroll över fordonet. Men det finns ingenting som säger att föraren måste befinna sig i fordonet. För varje fordon eller fordonskombination i rörelse så finns det ett flertal lagar som man måste förhålla sig till. Det måste finnas en förare som i varje ögonblick har kontroll över fordonet. Men det finns ingenting som säger att föraren måste befinna sig i fordonet.
Hallå, hallå, 1, 2. Hallå. Yes. Hallå. Vad har hänt med den här nu då?
Jag är med i alla fall.
Yes, vi ska se här.
För varje fordon eller fordonskombination i rörelse så finns det ett flertal lagar som man måste förhålla sig till. Det måste finnas en förare som i varje ögonblick har kontroll över fordonet. Men det finns ingenting som säger att föraren måste befinna sig i fordonet.
Talk about remote controlled timber loading. And before we start, I once again would like to remind you that if you want to ask questions, please go to menti.com and use the code 61586353 to ask your questions, and we will take them in the end of the presentations. But now, in November 2021, a remote-controlled timber load was tested for the first time in Timrå. And now we're gonna go back to Timrå in Torsboda and look how it looked like.
För varje fordon eller fordonskombination i rörelse så finns det ett flertal lagar som man måste förhålla sig till. Det måste finnas en förare som i varje ögonblick har kontroll över fordonet. Men det finns ingenting som säger att föraren måste befinna sig i fordonet.
I leave the word to you, Tanja.
Thank you. My name is Tanja Keisu, and I'm here from Biometria. What is Biometria? Maybe some of you are thinking. Let me give you a short brief. Biometria is a member-owned association operating in the forestry sector. We do impartial measurement and detailed reporting about the wood flows all around in Sweden. For an example, we communicate with over 3,000 forest machines every year, and in that communication, we handle detailed information of over 200 million trees being harvested. I am head of Biometria Labs, our department for innovation, where things like remote-controlled vehicles makes us very curious. But how did we go from measurement of timber to join this project about remote-controlled timber loaders? Biometria was inspired by the mining company Boliden back in 2018, when they, together with Volvo construction equipment, announced that they had developed a remote-controlled wheel loader. That was at the same time as the forestry sector was in a big transformation regarding measurement of timber. Since the 70s, timber have been measured on site at the industry, but a remote measurement method was developed and the measurement was moved to remote centrals. There were several driving forces to this transformation, but mainly to lower cost and higher accessibility. Now, 5-7 years later, we can see that remote measurement shortens waiting times, enables longer opening hours, because different industries can share the same operators. We see that the truck fleet in the sector can be used more optimally, and Biometria have staffing 24/7 for measurement. And there is this vision in the industry to have a wood flow everywhere in Sweden 24/7. And remote measurement and remote unloading are linked. After measurement, we do the unloading. But we can't do things just for fun. There needs to be a business need. But before I pop into the business need of this project, I would like to share a challenge we have in the forest industry with our raw material. As you know, Sweden is a large country with long distances, and our raw material trees grow everywhere. Transportation can't be done only by timber trucks. For long distance, we need to use both railway and shipping by sea. But we don't have railways or seas out in every forest, so the first part of the transportation is always made by timber trucks. And we have these timber terminals for temporary storage before the raw material is transported to pulp mills, sawmills, or heat plants. And that's why we have measurement sites in rural areas. And in these areas, it can be a bit tricky to find workforce or offer accessibility at nights or weekends. So the business needs for this project is to reduce cost, higher accessibility, and of course the work environment. It is a lonely environment and also a bit dangerous with these big machines operating. Quite same business needs as we had for remote measurement, and that's not strange because the industry is the same. And the vision of a 24/7 wood flow is also the same. At Biometria Labs, we are curious to look at the whole potential. What if every site that have remote measurement shared one central for remote unloading? How many operators would be needed? So here is a random pick day. You can for every hour see how many loads are incoming. They will appear as green dots on the chart. And we have then done a simulation how many operators would be needed for that. And this is a very upspeeded video. You can see there is a peak in the morning, around lunchtime, and in the afternoon. And it's a nice thought that an operator first could help someone up in the north of Sweden with unloading, and in the next second help someone down in the south of Sweden. So there is a great potential, but I think it's time to dig even deeper into the technology tested and the results of this project. Thank you.
All right. All right. Thank you, Tanja. All right, so my name is Christian Spjutare, and I work as a program manager for service solutions within construction equipment. And I will try to give you some background to how we work with this technology and show you some of the equipment we have been using and what we have been working on in the project. But let's start with some basics first. What is remote control? Well, we actually distinguish between two different types. When we talk about remote control, we actually refer to the traditional way, like when you drive a remote control toy. You use some sort of control device to maneuver the machine while it's within line of sight. But the technology we are working on here, we call teleoperation. And this is when you use cameras on the machine to transmit the environment to the operator sitting in a control station, which can be located completely independent of the machine. And of course, to do this, you need to combine a lot of different skills and know-how in areas such as communication, video processing, machine functionality, and not to forget, understanding the operator behavior. So why are we working with teleoperation? Well, as you saw before, Tanja mentioned some of the possibilities for using teleoperation in the forest industry, and I will come back to that. But there are actually several other interesting use cases where the teleoperation could improve our customers' business. And first, and perhaps the most obvious, is when a machine has to work in a hazardous environment. And you still want to keep up the production, but you want to move the operator away from danger. This can, for instance, be on steep ledges where the machine is at risk of falling or where the ground could collapse. Another interesting use case where teleoperation could increase the productivity is in mining, just as Tanja mentioned before as well. You can minimize the standstill after blasting in the mine. And instead of waiting for dust to settle and to ventilate toxic gases, you can move in and start working much sooner. And then teleoperation can also be an enabler for the transition towards autonomous operations. You can use it to aid in complex situations where the autonomous system is not yet fully capable of handling the situation, and let autonomy handle the more repetitive work steps. So why did we decide to go into the forest industry then? Well, since we have been working with teleoperation in a number of projects over the last couple of years, but in other applications, we said we needed to look into other opportunities. But from an operator perspective, we know that timber handling is a very difficult application to master. And if we could make teleoperation work in this application, we could probably handle many other applications as well. And also, this industry provided a new type of use case for us, where the machines on many remote sites could be controlled from one centralized tower. As Tanja also mentioned, there is a shortage of skilled operators, which is of course then made even more difficult by the remoteness of many of the terminals. Then teleoperation could help the companies to find the right skills by locating the control center in a more attractive place. And in a nutshell, this means that teleoperation could be an enabler to lower cost by co-locating the operations for the terminals, increasing the opening hours and providing cleaner, safer and more attractive work environment, of course. All right, so let's dig into the gear then. Well, first of all, when running a machine without an operator in the cab, it's of course extremely important to consider safety aspects. The major concern is to make sure that people can't enter into the working area unintentionally, believing that the machine is standing still because there is no operator in the cab. So this means that we need to use barriers to shield the machine in the working area. Taking a look at the machine itself, what we have been using for the tests in this project is a wheel loader called L180H high lift. This is a specialized machine for timber handling. It weighs roughly 38 tons. It can carry almost 9 tons of timber in the grapple, and it can place the timber in piles up to 6 meters high. And this machine was taken straight off the production line in our factory. And of course, that's where the fun started, getting all the gear in place and making it work together. So the machine is a standard machine which we have equipped with an additional PC and 5G equipment to be able to transmit both the machine control signals, but also the video streams from the cameras. The machine was then equipped with cameras to secure optimal visibility around the machine. The setup for this machine consists of 11 different cameras mounted all over the machine to cover the important angles. And the number of cameras here also reflects the complexity of this application, because for other applications we are using around 6 or 7 cameras generally. So if you have ever been in one of these machines, you know that visibility around the machine is quite tricky. There are a lot of things blocking clear sight, both forward, where you have the lifting framework, you have the protective grille over the windshield, backwards, where you have the long engine compartment with exhaust pipes, fire extinguishing equipment, and also down on the sides. It can be very tricky to see the ground close to the machine. So let's have a look at how we can improve the operator environment. Looking at the control rig, it consists of a standard Volvo training simulator, which provides a comfortable working position and the same type of controls that you find in the standard machine. And in front of that, we have placed 5 large screen monitors where we dynamically can change view positions, information presented to the operator and so on. And in this case, we had a mix of video streams and graphical representations like machine angle, distance to objects, rev counter, etc. And as we mentioned before, visibility can be a struggle in the machine, but one of the great advantages of teleoperation is that you have the possibility to significantly improve visibility for the operator. And by placing the cameras in the right spots on the machine, the operator can have all the information right in front of him, and no need to turn the head, look at the sides or to the back. Everything can be captured in one glance. There is, however, an important aspect to consider there, that the operator must not be overloaded with information, because even if the information is there on the screen, it might not be noticed if there is too much going on, attracting the attention. And to secure the best camera placements and of course also capture all the needed information for the operator, we performed a visibility analysis. And later during the development, we also had 2 sessions where the operators that would participate in the demo tested the machines and gave us feedback in an early stage, which resulted in a lot of changes to both the camera positions and the view placements on the screen. All right, so what input did we get from the operator then? During the demo week, there were a lot of people visiting, and we got many thoughts and ideas from them. Many of the reflections we hear from almost everyone testing teleoperation for the first time, like, I miss the sound. They want to hear the engine revving, the hydraulics working, to understand how the machine is working. I feel dizzy is quite common as well. I miss the sense of depth as well, since it's a screen and not a 3D environment. And it's important to highlight that many of these comments actually change as the operator gets used to driving, and some can actually be trained away with more practice. A really important comment was that this actually makes the work accessible for people with physical challenges, which was an actual case in one of the sister terminals here. And one common input from experienced drivers is that they want the screen view to be exactly the same as the one they are used to from driving the machine. And in this case, despite the protective grille over the window, which is actually blocking much of the visibility, the operator still wants the same view. And the reason is that he uses the protective grille and the lifting framework as references, and he knows angles and distances related to it when he operates the machine. So during the course of the week, we actually saw that this changed, and the views that they used the most were not the same in the beginning of the week as it was at the end of the week. And this really shows how important it is to give the operators time to learn how to run the machines teleoperated. It's almost like learning a completely new machine. Also, the first few days improves the driving performance dramatically. And we saw that the operators with fewer hours in this type of machine had a lot easier to adapt and learn to drive this machine, teleoperated. So to sum up, we got a lot of useful information and feedback from these tests, but to be able to realize a teleoperation solution like this, we also need dependable communications and robust communication and data transfer. So over to you, Mattias.
Yes, then I will go into some of the results and insights that we got from this project, and also some specific results from the evaluation of using 5G for this application, which was one important part in this. So if we look at the test site, we simplified the problem quite a lot. So we had one area here, 200 times 50 meters. That was the test area, where we had specific 5G base station installed with line of sight for the full area. And when you set this in perspective for the full timber terminal, it's quite limited. So the full problem is a bit bigger. Another challenge is, which I'll come back to, that these timber bundles are quite high, quite narrow, and the timber is excellent damping of radio signals. So this is a challenge that needs to be addressed. The setup for the communication is that the machine was connected with a 5G connection, and the 5G connection was installed just for this test, so it was line of sight and very close to the machine. Then a fiber connection down to Stockholm, and fiber connection back from Stockholm to Timrå to the control station where the driver was sitting. So the driver really was sitting here, not seeing the machine, but for simplicity of the test, this was quite important, I think. But the test shows that the data traffic moved back and forth to Stockholm, so basically it could be anywhere in Sweden. One of the main insights in this was that the communication, the 5G connection, it's quite sensitive when it comes to line of sight, especially when you have these timber bundles. And we had these requirements around 50 megabits per second that the application needed, and also end-to-end latency of 200 milliseconds. And what we saw that when we didn't have actual line of sight, we didn't fulfill the requirements totally. So that's a challenge that needs to be addressed to make this working, that you, for the full timber terminal, you have line of sight connection with the 5G connectivity. Other conclusions, because apart from what Christian was showing with setting up the machine to be teleoperated, which is perhaps the key thing in this to demonstrate. The other part is to show or investigate from this test compared to with manned machines. Is there a possible savings? Is there a business for this? This was one of the key questions in the project. And from the test, where we have measured man operated with the man inside the cab and also the teleoperated, is that with the savings you can do with teleoperation, there is a potential for efficiency improvement of 35% during day and 48% during night. Under one assumption, that some of the issues in performance can be solved. That is, we saw in the timing of certain parts, mainly of the grabbing and release of the timber. That took a bit too long to make this economically functioning. But the conclusion is that with more training, probably that could be solved, and also with automation, it also can be solved. We also had an activity looking at the legal aspect of this, and the main conclusion is that there is not really any legal issues to prevent this from happening. One needs to ensure that it's cyber secure, it's physically secure, that we don't hurt people. So basically that we need to create an autonomous operating zone. The communication, line of sight is needed to get good enough connection in this hard environment. Another thing which I don't think we really tested is to get the full end-to-end quality. I think we had perhaps too good connection in the backbone to really test this, but to get to a public network where we could have a lot of other traffic, there is also need to look at how to ensure the end-to-end quality in the communication. Oops. As Christian was said, the drivers at the end of the week got really good performance, apart from some parts of their work. They expressed some need from haptic feedback to feel the movement of the machine, and also sound. But also in the analysis we have made, it's that automation of these key tasks could solve a lot of these performance issues that we saw. So in the next step we will look at, so here we see the machine unloading into a train cart or a simulated train cart. So this was one of the tasks that took quite some lot more time to perform than the man equipped machine did. But here we have looked into that this could be automated. The other part that we will continue to look at, where we have formulated the project, is to look at the planning and distribution of the 5G connection to really ensure that this is in high quality and line of sight, and then also look at the backbone network to get an ensure the quality of the communication channel end to end, and get the technology in place for that. And also look at the edge computing technology for trying to see what parts can be handled in the edge, so we get better performance. And the other part that we will also look into is automation of these critical tasks. Because if these two parts are solved, I think it's then most of the challenges are solved to get this to happen someday. And this is the people involved in the test. We had Telia that provide the 5G connection, Skogforsk and Biometria that did the analysis together with SE, looked at the business models for this, and Volvo that equipped and manned the machine, and we that looked at the 5G connection and the future perspective of this. So this was the remote timber project.
Thank you so much. We have a lot of questions here on Menti. Maybe we can connect Christian also to the room so we can ask him a question. Welcome. Yes, we see you. Okay, I take them one by one. The first one, do you know if there is a gas sensor to detect leakage of oil around the machine in the working environment? Is that for you, Christian?
Yeah, that's actually one of the good and interesting topics we need to solve to take this further and putting it in a more large-scale scenario, because the sense of sound is one thing, the sense of smell is another thing that you commonly use when you operate these types of machines. So at this moment we don't have it, but that is something we are looking into for sure.
Yes. And we also got some questions here about VR and VR glasses and display and 360 view camera investigated. Was that investigated as a potential solution? And what was the reason not using VR?
Basically, we have tested a lot of these different options. We have tested VR, we have tested like dome displays and so on, but we have basically said that VR in this setting is kind of complex, and it gives even more the feeling of being dizzy and getting a little bit nauseated by driving the machine, since you are disconnected from the movement of the machine. So in this project we chose to not use that, and also for the dome display and so on, we chose not to use that due to the lighting conditions.
Yes, thank you. I will ask the questions, and anyone who feels ready to answer it, raise their hand. So, what is the acceptable range for delay that you can call the remote control is real-time remote controlling?
I guess that's one for me as well.
Yeah.
Perfect.
Yeah, we have made many tests on this, and as I think Mattias mentioned here before, 200 millisecond delay is the limit that we set end to end, from that you move the control in the rig to that you see the motion happening on the machine. So end to end, and that includes, of course, then also machine delays and so on.
I think this is in the same area. What's the latency including machine control system and human delay? If not, what was the total delay?
We haven't measured the actual delay in this system. Well, we saw that in the communications link, we could see that the delay was around 20 to 30 milliseconds, something like that. The other ones we haven't measured.
Yeah, I go on here. Is it possible to use this remote tech for, say, forklifts in shipping docks?
I would say this type of technology would be usable for basically any type of machine that you have.
I'm not sure who mentioned the security barriers. Do they have to be a physical, or have you looked into virtual barriers, person detection?
Those were some of the conclusions we did in the project, that is, of course, a feasible solution as well. For this project, we said that the most important thing is keeping people out of the demo area, and also that we weren't putting the highest focus on developing those solutions. We were developing the till operation system, but going forward in this, we of course need to consider those systems and developing those as well. But I mean, geofencing and people detection and so on is of course one of the interesting things to look further into. Now I hope there's a question for Tanja or Mattias here.
Yes. I'm not sure. It's another one. How far away is automation of all the different tasks like grip, grab, unload? Is that Mattias' question?
I think as Mattias mentioned here, we see that there are different areas of the work tasks that could benefit from being automated, definitely. And I mean, how far away is the automation of the complete one? It's difficult to say. We cannot really answer that now, but we have identified good steps to develop this application further, at least.
And what also that we discussed is that the automation could also benefit where you have a person in the cab, not only the teleoperator. That you can improve the quality, the work quality, even if the person is sitting there to get these functions there.
And I think one of the keys that we mentioned here also was that using teleoperation will be an enabler to actually get automation into the process, which will also speed up the development of that. So then you can handle the complex maneuvers with the people teleoperated, and then you can leave the either semi-automated support to automation, but also the bulk of monotonous work, for instance.
So when can we see this remote control loading in reality? Tanja, do you have any guess?
Well, I think we first need a couple of years of more research to look even deeper into the things that Mattias highlighted. But I think there will be an interesting race to be the first one with this technology on site, and that's not quite long in the future, I think. 5 years maybe. But then we have this perspective that going from measurement on site to remote measurement took 50 years. So yeah.
Hopefully faster than that. Yeah. So I have one more for Christian. What have you at Volvo learned during this project?
Well, I mean, we have so many learnings from this. I think one of the really important things to mention is the collaboration with the other partners of this project, which has been, at least from my perspective, a great success, combining the competence from the different parts of the industry and the value chain with the academic research. And I think this is a really good way for all companies to work to explore future business and technology potentials. So that's one of the key takeaways for me personally.
Yeah, and Mattias?
I can just agree that the collaboration in this project has been really excellent, and every partner has have a really important task to fulfill to make this project successful, and a good project leader. in Anna Maria.
Okay, I don't have any more questions now on Menti, I guess. If someone wants to ask a question here on site, yeah? You can use my microphone.
You talk about the different technique like 5G and edge you are going to use in the field. I am wondering if you, as I know, 5G cell can cover 100 meter. So in the industrial field, for cover a long area, you need more than one point site for covering long range. So if you miss the connection between the site and the machine, for example, in the machine located in the bad handover coverage or fading or something like this, you missing the line of sight between the machine and the sector, what will happen? And or if you miss if you have an outage between the sector, between the base controller of the DOS site and the Stockholm, as you said, it's a fiber. If you have a outage in the fiber connection, what will happen? And how you calculate the delay of this fiber, because at different time, it's because of the workload, we have different delay. So those things is so important. Missing connection between the operator till machine. How you solve this?
I mean, I think for the robustness of the end-to-end communication, I mean, that's what we're trying to address in the next project, that this is really important. But when it comes to the 5G connection, I would say, I mean, it depends on what 5G and what frequencies you use. You can get more than 100 meters. That's no problem. But what we learn here is that you need to plan the deployment of the 5G network on site quite well. And also we will investigate ways of improving that connectivity with masts, or if it's drones to help the connectivity there.
I can comment from a machine level that we have included a safety function related to that to make sure that if we have a too long delay in the communication, so we have a communication break, then we have an emergency stop on the machine.
Yeah, we got one more question.
Yeah, just related to that then, how do you control the delay of the video? How do you know that the picture the operator sees is actually the picture that the camera is taking for that moment?
That is also one of the things that we have incorporated with the sync here between the video and the control signal, so that we have a continuous check of that to make sure that there is a sync, and if we don't have the sync, then we also have put an emergency stop to the operations.
Yeah, I think there are no further questions then. No. So thank you very much, speakers and the audience.
Thank you.
We will now have a short break, and at 14:30 we will start with IoT-teknik för hållbara transporter in Swedish here. And in the next room, Vattenfall, they will talk about batteries, and that will be in English, so you know. So short break, and then we will start.
Då är vi redo att köra igång. Välkomna allihopa. Jag heter Daniel Adelander och jag kommer vara moderator på det här spåret. IoT-teknik för hållbara transporter. Jag har med mig 3 talare idag. Det är Sebastian Bader på Mittuniversitetet som kommer prata om utsläppsmätning av entreprenadmaskiner. Jag har också med mig Lundgren som kommer att prata om AI för mätning av bränsleförbrukning i bussar. Och så har jag med mig Emilia Rapp från Ånge kommun som kommer berätta om deras arbete kring att ta fram framtidens kollektivtrafik i en väldigt glesbygd. Om ni har några frågor, vilket jag verkligen uppskattar om ni har, och jag uppmuntrar att ni ställer de frågorna via menti.com. Använd koden 6158 6353. Det är bara att ta upp mobiltelefonen och gå in på den hemsidan. Så fort ni har några frågor skickar ni bara iväg det. Så kommer jag få upp det på min platta och så kommer vi ställa de frågorna när det är dags för frågestund i slutet. Vi kommer inte ha frågor mellan talarna utan bara efter. Så att ni är beredda på det. Och med det tänker jag bara att jag lämnar över ordet till Sebastian Bader.
Perfekt. Tack så mycket. Ja, som sagt, jag heter Sebastian Bader. Jobbar på Mittuniversitetet som universitetslektor och docent i elektronik. Jobbar då vanligtvis väldigt mycket med sensorsystem. Jag ska bara hoppa till första bilden då. Ja, jag ska prata om ett pågående projekt. Vanligtvis har det mycket längre titel än det här, men det blir väldigt krångligt så vi använder oftast utsläppsmätning av entreprenadmaskiner som en kortfattad version i alla fall. Det blir lite praktiskt. Som sagt, det är pågående projekt så vi har börjat i år. Vi har kommit ungefär halvvägs kan man väl säga, så det blir inga slutresultat här men lite mer berättelser om vad projektet handlar om och varför. Projektet är finansierat av IoT Sverige som är då finansierat av Vinnova, Formas och Energimyndigheten tillsammans. Så det första man kan fundera på då är men varför ska vi hålla på med utsläpp och entreprenadmaskiner? Någonting som man kanske alltid uppskatta eller upptäcka när man jobbar med någonting nytt är hur många saker det finns av det. Så nu när vi börjar jobba med entreprenadmaskiner ser jag entreprenadmaskiner överallt kan jag säga. Och varje gång jag ser en entreprenadmaskin tänker jag men det är roligt, där ska vi mäta någonting på och liknande. Men 2018 har Naturvårdsverket gjort en rapport eller en undersökning kan man säga och tittat just på vad de kallar för arbetsmaskiner men som innehåller då en väldigt stor andel entreprenadmaskiner, typ grävare och lastare och liknande. Och tittat just från perspektivet och utsläpp. Och de kom då fram till en stor siffra egentligen, 3,5 ton växthusgaser under då ett år som de har tittat på 2016. Om man tänker då vad betyder det här 3,5 ton, men då är det 6% av den totala utsläppen av växthusgaser som Sverige har. Så det är en ganska stor del. Och det är 20% då av transportsektorn. Om man tänker på vad ingår i transportsektorn, flyg och allt sånt, men där är 20% en ganska stor andel det också. Men det som är egentligen mest intressant är ju då att det används ju idag inte alls som någon typ av mätfaktor. Så om man tänker på entreprenadmaskiner, upphandlingar, projekt, byggarbeten, man tar inte hänsyn i princip alls till den här faktorn. Man gör en ekonomisk upphandling. Så vad är problemet? Så om man säger då lite kort, projektet handlar ju då självklart om att titta på vad skulle man kunna göra och hur skulle man kunna uppskatta det här. Så vad är problemet? Jag vet inte om man ser den här bilden, den är lite, när jag växte upp, ni hör kanske att jag inte är uppväxt i Sverige, jag är uppväxt i Tyskland och då hade vi sådana parkeringsskivor, finns ju fortfarande här, men det var väldigt vanligt att de på baksidan hade då man kan nästan tänka som en liten räknare. Så man kunde sätta in hur mycket man har tankat, hur många liter och hur många kilometer man har kört och sen kunde man avläsa från den skivan då hur många liter per, säg 10 mil till exempel man har kört. Så man fick egentligen ett effektivitetsmått. Och det är ju egentligen det som är mest intressant. Det är ju inte den totala utsläppen i princip som man tänker på, men det är ju att utsläppen ska ju på något sätt vara proportionellt. Det ska ju vara rimligt utsläpp så man har en effektivitet i princip. Man gör en viss aktivitet och sen har man ett visst utsläpp kopplat till det. Och det vill man ju förbättra effektiviteten. Självklart ska man inte förbruka så mycket om man inte gör så mycket, men det är acceptabelt att man förbrukar mycket när man gör en hel del saker. Så om man då tänker på det här bilexemplet som jag pratade om här med den här skivan, då är det ju ganska enkelt. Aktiviteten är körsträcka. Det finns egentligen bara antingen kör du inte eller du kör, och när du kör då kommer du en viss distans och du har en viss aktivitet. Tittar man då på entreprenadmaskiner, då finns det ju mycket fler olika aktiviteter. En grävmaskin den kör ju inte bara, men den gräver ju till exempel. Den gör ju en viss aktivitet. Den kan också stå still i tomgångskörning till exempel. Den kan kanske göra lite olika grävningsarbeten till exempel. Så det som är mycket intressant för oss i det här projektet då är egentligen att titta på hur kan vi relatera de här olika aktiviteterna till förbrukningen som man har, eller utsläppen. Jag pratar nu oftast förbrukning av bränsle, för det är ju i princip ekvivalent till vilken utsläpp vi då får för en viss specifik maskinstyp. Så det som vi egentligen tittar på i projektet, om man kommer till det är ju som ett första skede egentligen ett förståelse. Vad är egentligen utsläppen som vi har och hur kopplar de till olika aktiviteter? Och då handlar det ju, som ni kanske ganska snabbt förstår, det är kanske anledningen varför jag står här som någon som jobbar mycket med sensor- och mätsystem, om mycket datainsamling. Vad kan vi få för data och vad kan vi få för information om just aktiviteter och utsläpp? Och då har jag i princip satt här 3 olika delar där man kan i princip redan idag få data ifrån, eller som vi ser att vi skulle kunna få data ifrån. Så det första, jag kanske tar min pekare här, så första här, nummer 1, det är egentligen att moderna entreprenadmaskiner, de är i princip redan uppkopplade. Väldigt många av dem, tittar man på Volvo, Hitachi och liknande tillverkare, de ger en möjlighet att kunna få data redan idag av maskinerna. Men det är bara en del av datat, och det har också en stor utmaning att det är väldigt tillverkare specifik. Så i princip har du en Volvo-maskin, då får du ett Volvo-portal på webben där du kan logga in och titta på till exempel vad hade du för genomsnittsförbrukning av bränsle under en dag. Har du en Hitachi-maskin, då har du ett Hitachi-portal och gör precis samma sak. Men har du en vanlig entreprenad, då har du väldigt många olika maskiner. Och då har du ett portal för varje. Och det har i princip lett till, som vi har märkt under projektet, att ingen tittar på de här informationen för att det blir för krångligt. Så en sak som vi tittar på i projektet är just då att hur kan vi få det här datat ihop så att det blir enklare för en entreprenad som har olika maskiner. Men det är i princip data som vi redan har tillgängligt. Den andra punkten här är då att den här uppkopplingen som redan finns, den innehåller inte all data som finns i maskinen. Så en maskin, samma som en bil, har ett datorsystem kan man säga som samlar väldigt mycket information. Där vi kan lägga till i princip extra instrument för att läsa ut redan befintlig data och samla den datan. Och på det sättet skulle vi självklart kunna få mer information om vad en maskin gör. Skulle kunna till exempel titta på varvtal, alltså hur aktiv en maskin är, men också vägsträcka och liknande, och självklart bränsleförbrukning. Och den tredje är då kanske lite mitt område om man tänker lite mer framåt. Vad finns det inte redan nu i maskinerna för data? Men om vi lägger till nya sensorsystem, vad skulle vi kunna säga då om aktiviteterna för en maskin? Och då tänker vi oss lite grann om ni känner om smart klocka. Den samlar ju väldigt mycket information om mest om kanske rörelseinformation. Och i princip samma sak skulle vi kunna använda på en maskin. Alltså liknande sensorer, samla in rörelsedata, gör analysmodeller på det och komma från det då till lite mer klassificering av aktiviteter i princip. Så det är lite mer den datainsamlingssidan. Den andra sidan är då, vad gör vi med den datan? Och då har vi tittat i projektet, genomfört några workshops, bland annat med Pro, som har skrivit en rapport. Så om ni vill ha mer detaljer om det kan jag rekommendera den här rapporten. Den kan jag gärna skicka till er om ni vill ha. Så ni får gärna höra av er till mig. Men vad man egentligen kan titta på, jag vill inte gå in i detalj på grund av tid här, men vad man kan se är då att det finns olika vägar hur man skulle kunna använda den här aktivitetsinformationen och bränsleförbrukningsinformationen eller utsläppsinformationen för att minska då utsläpp. Och det kan man väl säga då från ett lägsta nivå på något sätt, alltså inte lägsta nivå där det är minst minskning, men lägst, alltså närmast maskinen om man säger så. Kan man självklart göra väldigt mycket på maskinsnivå. Man kan göra till exempel på personer som kör maskinen. Självklart insatser, att man satsar på utbildningar. Man kanske upptäcker baserat på datat att olika personer kör olika effektivt, till exempel på olika aktiviteter. Men man kan också tänka sig, om man går mer på den här högre nivån då, en mer allokering av maskinerna. Alltså att man ser kanske att vissa typer av maskiner är bättre eller effektivare på vissa typer av uppgifter. Så sist vill jag bara kort nämna vem som är med i projektet. Det är ju som sagt lite olika delar i projektet, så det finns ett behov för olika roller. Det är inte allt vi kan göra självklart. Men man kan generellt säga att projektet har i princip två delar, och det är väl lite de här två delarna som jag just pratade om. En mer teknologidel där vi tittar på datainsamling och utveckling av nya teknologier, och sen kanske en del som är lite mer kopplad mot behov och affärsmodeller och affärsutveckling. Tittar man då på den behovs- och affärsutvecklingsdelen, då är det då Sundsvalls kommun, Region Västernorrland och På som är med. På teknologisidan då är det Portal Plus, så ett mjukvaruföretag som tittar väldigt mycket på hur får vi ihop de här olika dataströmmarna, alltså olika källorna för data i en plattform. I Magimap är ett företag i Stockholm som tittar på dataanalys, och sen vi som kanske mest har den här sensordelen. Och sen som sist men inte minst har vi Bron Innovation med som projektledare oss i det här projektet. Så här slutar jag. Jag får inte ta frågan nu, så jag hoppar över den här och ger vidare till Jan.
Tack. Ja, här får man prata effektivt. Det här länkar i, kan man säga, det som Sebastian har pratat om också. Jag ska nämna någonting om AI för minskad bränsleförbrukning. Och då är det ett projekt som vi hade för något år sedan tillsammans med Portal Plus som var projektägare, och så hade de Byberg Nordin med sig i projektet, och så kom vi in då och gjorde en liten sån här, vad heter det, PID, eller vad heter det, för att testa AI-modeller på bränsleförbrukning. Och då handlar det om att man tar då liksom, inte nästa steg, men det blir en annan del av det här. För i vårat fall då hade man redan loggat bränsleförbrukningen för olika bussturer. Och bussturerna är ju liksom fasta linjer som alltid går på samma ställe på något sätt. Så för en maskininlärningsperspektiv då, så var det väldigt bra. Man fick många datapunkter på samma linje. Man hade bränsleförbrukningen som någon typ av sanning då, kan man väl säga. Och då var tanken då att man skulle kunna förutsäga hur mycket bränsle det skulle gå åt i framtida bussturer. Och en tanke som också kom upp då var om man då skulle kunna optimera kanske. Man sätter en viss buss med en viss förare på en viss tur för att optimera det här. Och då kommer man in på det etikområdet direkt. Då är det som, då vill man inte ha med namnen vid vilken bussförare det är. Så där. För jag kan avslöja redan nu att det var den faktor som hade störst betydelse i den här undersökningen. Så vi gjorde en prediktering av bränsleförbrukningen, men också en prediktering av restid, för det är också intressant, framförallt för ett företag som alltid ska vara i tid på något sätt. Så det här hade ju också att göra med vilken sträcka det var, vilken förare och vilken buss och så vidare. Bussen hade väl kanske mindre impact just där då. Och hur många variabler utav de här som man hade då? För man har ju massor med sensorer och data som kommer in då, så det var ju, tror jag, över 20 olika variabler som man hade att leka med. Vilka av de här ska vi välja då? Vilka hade bäst impact så att säga. Det vi såg tidigt var, och det här kan man ta med sig till andra projekt också, att allting som hade någon typ av ID, ett fordons-ID till exempel, säg att man använder sig av nummerplåten eller något annat sånt där som i stort sett är helt random. Eller bara om man använder sig av personnummer eller någonting sånt, så har ju det ingenting att göra med bränsleförbrukningen egentligen. Det finns ingen koppling mellan den faktiska koden liksom, och förbrukningen. Så det vi såg var att man hade då liksom fall som det här, där man hade liksom ID upphackat och så fanns det något ID här uppe liksom, och det var väldigt tomt emellan här. Och det fick en väldigt stor påverkan på predikteringen, framförallt när man inte använder neurala nätverk utan man använder tidigare modeller som support vector machines eller någonting i den stilen. Och då såg vi att om man kunde sortera alla de här kolumnerna som hade någon typ av ID, sortera dem efter förbrukning, så kunde man öka på prestandan betydligt. Om man dessutom ersatte varje ID av medelförbrukningen för just det ID då, så kunde man nå, som vi såg, den bästa prestandan i det här. Och då gjorde vi en test med support vector machines och neurala nätverk för att se liksom prestandaskillnaden där också då. Och då när man hade gjort det här för processningen med ID, då var faktiskt support vector machines riktigt okej. Man nådde inte riktigt upp till samma prestanda som med neurala nätverk, men det var nära ändå i alla fall. Och här ser ni också alla de här. Det är 24 olika parametrar här då. Det står 25 här, men en av dem är den här, vad har vi den någonstans nu då? Ja, alltså hur mycket bränsleförbrukning det är. Så en av dem är det sanna svaret så att säga. Om man istället går in på neurala nätverk då, den typen av maskininlärning, så såg vi att för just den här typen av data, det är ju tidsserier egentligen. Det är ju inte bilder vi pratar om, det är inte ljud, utan det är då liksom datapunkter på något sätt. Även när det gäller ID så har man ju liksom en tidsserie på ett eller annat sätt. Eller om det är tid eller om det är plats då. Och då fungerar vad de kallar för brands med Bayesian Regularized Artificial Neural Networks kallar man det för. Fördelen är att de är ganska lätt att använda, för de är faktiskt svåra att överträna. Och överträna betyder att man slår i taket på något sätt. Man får ett svar som säger 100% egentligen då, korrelation, och då vet man att någonting har gått fel. För det är i stort sett omöjligt att nå. Så de är väldigt robusta och trevliga och liksom ändå lätt använda. Så vi kände att det här var ett bra case för den här typen av nätverk. Så gjorde vi en optimering för vad man kallar för aktiveringsfunktioner också då. Så i varje sån här liten neuron, en sån här liten nod, så har man någonting som man kallar för aktiveringsfunktion, och det här magin kommer in på något sätt i neurala nätverk då. Hur den här aktiveringskurvan ser ut, om den är väldigt spetsig eller om den är lite böjd så här. Det kommer att ta mig en hel kurs att gå in på varför det är så, men jag kan bara säga det, att det är där magin sitter på något sätt. Och sen om man gör det här till exempel i MATLAB då, så kan det se ut på det här sättet, att man får upp en nätverks karta på det här sättet då. I det här fallet kan det kan räcka med ett gömt lager till och med här. Man kan använda sig av 2 gömda lager för att få faktiskt ett väldigt bra resultat. Och här kan man se då lite grann vilken typ av felprocent man skulle kunna förvänta sig av det här testet. Ni ser i den här tabellen då, där man har X, då har man tagit med den parametern, som till exempel veckodag, timme på dagen hade stor betydelse, distans, typ av dag. Det hade att göra med om det var helgdag eller om det var röd dag eller några sådana saker också hade stor betydelse. Det jag också ska säga här är att vi hade 2 olika typer av turer. Vi hade korta turer där det var jättemycket data. Och sen var det ett långt hopp till väldigt långa turer. Och där fanns det inte speciellt mycket data utan det var bara lite grann. Och då fick vi problem i båda de här modellerna. Så vi fick hacka upp det här då och göra ett nätverk för kortare turer och ett för längre turer. Problemet är att de här längre turerna, det blir nästan lite grann som outliers. Så att man tränar nätverket i huvudsak på de korta turerna, men man försöker att liksom kroka in de här längre turerna också. Och då går noggrannheten ner. Men man ser att man var nere i någonstans 8% i alla fall. Så vi kom fram till en hel del rekommendationer till både Portal Plus och Biometria där man kan helt enkelt vi berättade vad vi hade hittat. Jag tänkte bara väldigt kort visa ett kodexempel. Det här är från MATLAB det uppsatta neurala nätverket. Sen de andra 30 sidorna kod, det var liksom så här förprocessa datat, sortera in allting, ni vet vanlig kodning liksom. Men just för att sätta upp det neurala nätverket, det var det här. Så ni vet ungefär komplexiteten av det. Ja, vi tar nästa.
Ja, hej. Emilia Rapp heter jag. Jag jobbar på Ånge kommun som hållbarhetsstrateg. Och jag brukar ju säga att jag har inte förstått hur liten kommun jag bor i förrän jag började jobba på kommunen. Så jag är ju också kollektivtrafikstrateg och infrastrukturstrateg också. Så det är i kollektivtrafikshatten som jag är här idag. Välkomna till Ånge, tänkte jag säga. Det är ju inte alla ni som bor i Ånge, så jag tänkte ta er på en liten tur vart vi är någonstans. Men så här har vi det i Ånge, mestadels av tiden. Det händer väldigt mycket hos oss nu, så att det är inte riktigt så här lugnt och skönt som hon här på bilden har det. Men mestadels så har vi det så här. En liten sån här snabb kurs i vart vi är någonstans och våra förutsättningar. Vi är strax över 9000 invånare i Ånge kommun. Förra året var första gången på typ 50 år som vi ökade i befolkning med 7 personer. Förstår ni vilken grej? Vi har en yta på strax över 3000 kvadratkilometer. Och det säger ju inte så mycket, men det är ungefär ganska exakt som Blekinge landskap. Så vi har en stor yta. Och så den här procenten där uppe till vänster, vi har 88% skog. Vi har väldigt mycket skog i vårt område. Och det ska vi försöka skapa en relevant kollektivtrafik i. Några saker till som kännetecknar oss. Det här är från det visionsarbete som vi gjorde för ett par år sedan. Vi har identifierat 3 kulturer hos oss. Hejkulturen. I Ånge kommun så hejar man på varandra på gatan. Det kan vissa tycka är jättekonstigt, men vi tycker att det är ganska trevligt. Vi fikar väldigt mycket. Kokkaffe har jag förstått. Det är inte alla som vet vad det är, men hemma hos oss så är det väldigt vanligt. När jag pluggade i Lund så var det en grej att, vet ni vad de gör i Ånge? Det var en kille som jag pluggade med som faktiskt hade släkt från Ånge. De kokar kaffet. Och alla bara, va? Vadå? Det här är alltså innan espressomaskinerna fanns i alla hem. Men det gör vi fortfarande. Och sen den här sista punkten som är också en del i det som vi ska prata om idag. Inga problem. Vi hittar lösningar och vi måste tänka utanför boxen. Och det är också det som vi tänker att vi ska göra nu också när det kommer till kollektivtrafiken. För precis som i mycket annat så är mycket av de lösningarna i samhället kopierade på samma sätt oavsett vilken geografi man befinner sig i. Och det funkar inte alltid så bra i en kommun som Ånge. Speciellt inte med kollektivtrafiken är ett klockrent sådant exempel. Och om man tittar på kollektivtrafiken som system, jag ska ta det här jättesnabbt, så finns det ju ett antal parametrar där som kollektivtrafiken bygger på. Att man har många människor i rörelse som skapar en god ekonomi och som gör förutsättningar för många avgångar och en bra tidtabellsupplägg. Och i en stadsmiljö så funkar det jättebra. För där har man dessutom svårt att hitta andra alternativ. Det kan vara väldigt trångt till exempel. Och det är korta avstånd och priset blir inte heller så högt. Men tittar man på det här i ett glesbygdsperspektiv så är det precis tvärtom. Vi har lite befolkning som gör att ekonomin för vår kollektivtrafik blir jättehög och tidtabellerna blir ännu glesare. Det är en buss in på morgonen till skolan och så är det en buss tillbaka på kvällen. Inte relevant för någon annan än för skoleleven. Så där behöver vi liksom ändra på tänket lite, tänker vi. Och så här ser vår kommun ut. Det är faktiskt så att de allra flesta i vår kommun, de bor i Ljungans dalgång i den här stråket här i mitten. Och här har vi en i storstadsbor så är det inte relevant kollektivtrafik, men för oss en relevant kollektivtrafik med mittstråket som går där med tåget, och vi har också ett antal busslinjer som går i dalgången. Men vi har också människor som bor ute i de här färgade områdena här. Och det är den här områdena som är, som ni sa i början, glesbygd. Här brukar jag jämföra oss med de byar som ligger här ute. Alltså det är precis som man bor på en ö ute i havet. Enda skillnaden med Ånge kommun är att man har skog emellan, det är inte vatten. Men man bor i en liten by, det kan vara 20 personer, men man har Naggen, de har väl inte riktigt 2 mil, men 18 kilometer in till Fränsta. Det ligger här ungefär. Och det är det här systemet som det blir jättekrångligt för oss när vi har en storstadslösning. Där en person som har färdtjänst blir skjutsad i en bil. Färdtjänst är ju om man inte kan köra själv, om man är äldre och behöver taxiskjuts. Och samtidigt så har vi ett skolbarn som ska åka hem. Nu råkar det inte bo något barn i Naggen, så det var ett dåligt exempel, men det vet ju inte ni. Och då åker de parallellt bredvid varandra. Och i en stad så kan man ju ha det så. Det är ju inga konstigt, inte så långa avstånd och det är mycket folk som ska åka och det sitter flera personer i samma bil. Men hos oss så kanske inte det funkar. Så då tänker vi så här. Att om vi skippar det här med att tänka tidtabell för de här färgade områdena och istället säger till de som bor i de här områdena att vid varannan timme under dagtid så kan ni komma in till de här svarta prickarna som ni ser här nere i dalgången, den närmaste serviceorten. Och de här resorna behöver ni boka, men ni vet att klockan 8, och klockan 10, och klockan 12 och klockan 14 så kan ni komma in till de här serviceorterna. Och toppen också är att det är precis när tågen går och när vi kan åka åt olika håll och vidare också. Men det är först när de här personerna ringer och bokar som man får reda på när man blir hämtad hemma. Så att istället för att man vet alltid vilken tid man ska åka hemifrån, så vet man vilken tid som man kommer komma fram till serviceorten. Då. Det här skulle ju göra att de här områdena som idag inte har en fungerande kollektivtrafik, det är ju faktiskt så, om man ska hårdra det, så är det så, bor man då i Naggen och är berättigad färdtjänst, så får man klockan 7 på kvällen åka och hälsa på en kompis, en väninna eller någon annanstans i kommunen och bli skjutsad i taxi. Men bor man i grannhuset och är 12 år och vill ta sig till fotbollsträningen, så får man inte åka. Och det är också det här som vi liksom vill komma åt i det här, att vi ska få ett mer jämlikt system. I en kombination utav de här typerna då. För vi tänker oss att de här resorna ska gå i den här typen utav fordon då, som är lite mindre. Och då fortsätter vi det här, hitta nya lösningar. Det här är också från visionsarbetet. Vi ska tänka lite större, ta lite kliv, tänka utanför boxen. Ja, det var snabbkursen i glesbygdstrafik.
Ja, då har ni fått höra snabbkursen av alla de här tre. Det har ju gått väldigt fort och jag tror nog att de hade kunnat prata 10 gånger så länge om allting. Eller jag är rätt säker på det. Vi har inte fått in så jättemånga frågor, så att nu får ni se till att få in lite mer frågor. Så tänker jag i alla fall att vi börjar med att jag vill höra lite hur ni tänker, Sebastian, Jan. Hur skulle ni ta er an den här utmaningen med att se till att man kommer fram där varannan timme oavsett vart man bor i det här området? Behöver man teknik för det? Vad gör man?
Ja, det är en bra fråga du. Får man examinera sig? Nej, men det som jag tänker spontant på, det är ju att det är ett logistiskt problem. Alltså man vill ju i princip kunna förutse hur mycket behov det finns vissa tider. Och där, jag tänker lite, det finns ju lite kopplingar till det som Janne pratade om, det här med vilken typ av dag är det till exempel, vad finns det för, kan man på något sätt förutse vilken typ av behov det kan finnas, men det blir ju inte alla typer av resor. Jag ser väl kanske spontant ingen direkt koppling till mitt huvudområde sensorteknik. Men det är ju mer dataanalys, databehandlingsproblem, alltså mer logistik som jag ser. Det är väl det som jag kan säga spontant.
Jo, men det stämmer ju. Och det är ju, här kan man ju komma in med den typen av predikteringsteknik också som vi har sett i andra projekt också, bland annat med bussturer och så vidare. Så det beror ju helt enkelt på vad för data man har. Och ibland är det inte helt uppenbart att datat har korrelation mot det man är intresserad av heller. Så ibland så kan det vara så att just det här med typ av dag, liksom, om det är en helgdag eller om det är natt eller något sånt, kanske inte är helt intuitivt att det har så stor betydelse, men vissa av de här sakerna kan man ändå bli lite förvånad över, så man har lite ett öppet sinne för vilka parametrar som kan få effekt. Det är mitt tips.
tänker en annan sak som jag tänkte på när du pratade, det var min studenttid kan man säga. Men man hade ju väldigt ont om pengar och i Tyskland fanns det då en webbsida där man kunde säga men jag vill ta mig idag från den stan till den stan, och sen kunde en annan person, som oftast en annan student som hade en bil och åkte från den stan eller i närheten av den stan till närheten av den stan, kunde erbjuda att ta med dig. Och ja, men den fick ju då lite pengar, vilket var jättebra för studenter. Och den andra studenten som hade lite pengar kanske resa lite billigare än med tåg eller liknande. Så man skulle ju också kunna tänka sig sådana lösningar. Alltså, en del är ju att men jag vet att jag vill ta mig den här tiden till den här platsen. Men ibland kan det ju också vara så att det är tvärtom, att man, ja, men nu är det någon som åker in, nu finns det en möjlighet, skulle jag vilja åka med? Alltså att man tänker att det finns ju kanske spontana möjligheter, att någon som inte planerar, jag måste ta tåget klockan 4, men ja, men finns nu en möjlighet att ta mig in till stan, så kanske jag åker med och tar chansen att ta en kaffe och träffa Kalle.
Just det, att det finns på busstidtabellerna finns med när Kalle slog på kaffebryggaren.
Det är den här tekniken kommer in som vi behöver.
Vi har en fråga direkt till dig, Jan. Tar man hänsyn till antal passagerare i bussen?
Jag har för mig att vikten var med i den här... alltså vikten finns ju med på något sätt i förbrukningssiffran. Men då blir det ju mera ett medelmått så att säga, och då har det att göra med vilken tidpunkt på dagen det är. Och, men ska man få en ännu bättre noggrannhet i det så ska man naturligtvis mäta hur många passagerare man har vid varje tur. Jag är osäker på om den siffran var med, jag tror inte det.
Har vi några frågor av er som sitter här i publiken? Det är inte så mycket som ni har skickat in.
Eller idéer hur man löser ångerproblemet.
Lös det åt mig.
Exakt. Ja, kanske inte har så många frågor. Jag tänkte också på att jag har hört att det fanns ganska stor potential till bränslebesparing genom det där. Har ni sett någonting om vad det finns för möjligheter?
Jag vet att Portal Plus har tagit det här vidare. Jag har inte hört så mycket mer om det efteråt, men jag vet att de har varit i kontakt med oss också efteråt. Så att de har tagit den här idén vidare. Tyvärr var det ju så att det var ju föraren som var liksom den största bidragande faktorn på något sätt. Och det är svårt att göra så mycket med det. Risken är att bussförare Bosse alltid får köra till Kälarne och tillbaka. Liksom. Det är ju som, man kan ju hamna i det läget. Då, så att det här är ju en teknologiövning och sen får man ta med de sociala aspekterna efteråt. Då. Men ja, det fanns stor potential.
Ja, det var vad jag hörde också, att man var nästan förvånad över det. Ja.
500 000 liter diesel per år. Ja, just det.
Ja, för det som är på distans och kanske inte hörde, Mattias sa att de kunde spara upp till 10% av bränsleförbrukningen. Så det är en ganska stor besparing för egentligen hela Byberg Nordin då, som kör över hela landet. Så enorm besparingspotential där.
Nej. Mm. Ska du eller jag sammanfatta?
Jag tänker om det är någon som kan svara på det här direkt. Så. Ja, repetera gärna.
Ta mikrofonen. Precis.
När är det tillåtet att samla in information om olika invånares aktiviteter över året egentligen? För man vet ju vilka som anmäler sig till olika idrottsgrenar och föreningarna vet ju det. Vilka som går på hembygdsgården. Ja.
Jag tänker, alltså vi som kommun vet ju väldigt mycket. Och speciellt då när det handlar om de här områdena så vet vi ju att det bor 17 personer i den här byn. Och vi vet att det är, och vi vet när fotbollsträningarna är, och vi vet också vart barnen bor. Så att jag tänker att vi har ju väldigt mycket information, och sen hur vi får använda den, det vågar jag inte svara på.
Men i och för sig kan du inhämta tillstånd förmodligen för att göra det, för att kunna publicera det, till information. Att nu och kanske också be föreningar samordna så att träningar börjar och slutar samtidigt.
Ja! Ja, och gärna direkt efter skolan så att man inte ska hem de där 3 milen och sen åka tillbaka igen.
Men då kanske de kan få en fika eller någonting annat under tiden.
Precis, vi måste ha lite kök där vid idrottsplatserna. Ja, det blir mycket frågor. Men det är precis de där tankarna vi har. Men vi är precis i startklubbarna, så det är väldigt bra att få höra era tankar kring det.
Det är en bra poäng där med om man ger sitt medgivande så att säga och så säger att det här blir någon typ av app eller någonting som man använder sig av, då kan man ju göra ganska mycket. Det gäller att man bara inte sprider personlig data till hela gruppen så att säga, men det är en bra poäng.
Verkligen. Nej, vi har inte kört någon pilot än. Vi håller på att söka pengar för att få liksom börja förstudiearbeta med det här. Så att det är verkligen i idéfasen. Men det har jag inte sagt. Men vår kollektivtrafikmyndighet Intur, vi gör det ju tillsammans med dem. Så att det är gemensamt arbete. Och att det här också liksom ska kugga i de upphandlingar som finns och så. Så att det är mycket som ska klaffa. Men jättespännande är det. Och framförallt för invånarna som idag inte kan ta sig. Och framförallt barn och unga faktiskt. Vi gjorde en undersökning förra året där 42% av högstadie- och gymnasieeleverna på våra skolor svarar att de inte kan ta sig till fritidsaktiviteter. Frågan var lite annat formulerad, men alltså det är jättesvårt. Och det är ju en jättestor fråga för oss vad gäller barns hälsa, att de ska kunna ta sig till fritidsaktiviteterna. Och då hänger det på att mamma och pappa skjutsar, och gör man inte det då blir man hemma.
Ja, jag tänkte bara en sak som jag tänkt på. Det borde ju finnas ganska många andra verksamheter som man borde kunna lära sig av. Alltså om man tänker posten, alltså i glesbygden. Alltså de måste ju ha väldigt mycket erfarenhet av att rotplanera baserat på vad de har. Alltså att hur jobbar de med sådana frågor? Att man tänker att man kanske tar med fler aktörer i en sån första diskussion än bara de som egentligen adresserar just problemet i sig, kollektivtrafik.
Ja. Kan vi
i alla fall på morgon.
Jag ska fråga Postnord om de kan ta med sig lite
pensionärer
och skolbarn när de ändå är ute och åker.
Ja, men det skulle ju kunna vara tvärtom.
Där har vi innovation på
men det skulle ju kunna vara tvärtom, att man tar med sig posten.
Ja, och det har vi ju bussgods också, så det finns också med i tankarna här. Nästa år? Nej, det är jättesvårt att säga. Jättesvårt. Men en pilot i kommunen, vi tror inte att det ska vara så himla svårt att få igång inom ordinarie avtal heller. Så att, bara för att få testa under en tid. För det är det också. Funkar det ens? Och det är också det här, går det att få folk att förstå vad det här är för någonting? Vi är så inkörda i vad kollektivtrafik är för någonting. Och så ska man helt plötsligt tänka på ett annat sätt. Att det handlar jättemycket om hur vi marknadsför det här också. Alltså att få folk att förstå vad det är vi menar. Så att vi inte bara pratar hur fordonen ser ut, vilket vi gärna gör i kollektivtrafiksvärlden, kan jag säga.
Ja, vi har inte mycket tid kvar här. Jag tänkte bara fråga Sebastian, vad tycker du är den största nyttan man kan göra med utsläppsmätning av entreprenadmaskiner?
Ja, största nyttan till slut hoppas jag väl att det blir en minskat utsläpp, självklart. Det är väl den största nyttan. Men just nu i första fasen är det ju ett förståelse av vart genereras utsläppen i princip i vilka aktiviteter, hur ser det faktiskt ut, hur mycket finns det, hur mycket ineffektivitet finns det, till exempel tomgångskörning, hur stor andel är det av en vanligt grävmaskin som står runt och gör sitt arbete. Så det är ju i första skedet förståelse, kunskap, till slut utsläppsminskning. Vilket ju i sig också självklart har ekonomiska fördelar för entreprenören själv. Så det finns ju inte bara miljöfaktorer att ta hänsyn till, men även det finns ju, alla vinner ju på det, om man säger så.
Ja. Med det tänker jag att vi säger tack till alla som har varit med här idag. Tack för att ni valde att vara med i det här spåret. Och tack ni som är på distans för att ni valde att vara med här också. Ja.